Thank you all for this nice opportunity to present this or give this talk. As Vivash pointed out, Professor Vivash pointed out, I will be trying to address the security aspects, or rather the insecurity aspects of Internet of Things. Um, because as we know that IoT is a resource constant environment, so how do you really, like address security in those scenarios? So I will be trying to slowly develop the idea of the talk. Okay, and I will start from uh, from concepts which are essentially well known and well established, and from there try to get into the hardware security aspects in the context of IoT security, and in general, how do we like authenticate in such or how can we potentially authenticate in such environments. I will be talking about some of the projects that we are doing, in particular with a very well established company in the domain of IoT security. And I'll be trying to some address on, like discuss about some of the solutions that we are trying to develop in our laboratory at IIT Kharagpur. So this is the rough agenda of my talk. I will start with background. So background means kind of giving the overview of why security in the context of IoT or cyber physical systems is such a growing concern. I will be trying to talk about, like in particular the area that I work on, which is called as side channel attacks, and how like IoT can really get devastated by potential side channel attacks. In this context, I will be talking about two important class of attacks, which are called as power attacks and fault attacks on the hardware devices which are deployed in the on the IoT environment. I shall be talking about authentication of devices, because we know that one of the big like challenges in the context of IoT is we have got potentially billions of devices which are getting interconnected. So how do we do like a trusted communication among them? Key exchange among these devices becomes growingly a complex problem, and therefore we need to engineer suitable solutions which can be ported on such kind of resource constant environments. I shall try to briefly conclude my talk with the final frontier of IoT, which is the cloud. So we all know that several of our data are all continuously getting like collected, and they are also being stored in the pervasive cloud, which is essentially a public repository, and that essentially immediately brings us to the concerns of privacy. Okay, and I will be trying to talk about some of the works that we are trying to address in this context, which are also extremely crucial for the overall success of IoT. So therefore, the gap that I will be trying to address is between theory and practice. So in theory, we know that we have, like a wonderful setup where there is a sender, say Alice, and a receiver, say Bob, who are communicating an information, and that could be any cyber physical system. Even the IoT essentially is not outside the scope of cyber physical systems. So we have got two endpoints which are distantly communicated, and there is an untrusted communication channel through which they are communicating. So classical cryptography tries, or classical like encryption, or the cryptographic primitives like hash functions and so on, tries to kind of gives you like certain assurances of confidentiality, integrity, availability in this kind of environment. However, cryptographic theory has got limitations, and there is an absence of theory for the reality. Like what will you probably do think of in theory, when you're implementing it, you will find out that there are gaps, and because of these gaps, right, even mathematically strong ciphers or strong cryptographic solutions will leak in the real world. So one of the potential leakage sources are what are called as side channels, and I will be trying to talk about some of them, which are very important, through which a cryptographic module can leak information to its environment in an unintentional fashion. So let me, like start with an example. So this is a, like a sort of a toy example, but is important to, like tell us what exactly is the situation. So this is, like probably nothing to do with IoT, but essentially, is an important gadget that we probably all of us use. So this is a locker, right? The e-locker, for example, that has probably been, like, been deployed in several places, in restaurants, in shops, and so on. So the designer, in theory, right, thought that okay, there is probably a 6-digit pin that you need to enter, and therefore you know that like if you are assuming non-zero pins, then probably there are 10 to the power of 6 minus 1 possibilities, and among them to get the correct pin is really hard. So that is essentially what the theory essentially guarantees us. But in practice, what can happen is, and in one of the, we just tried to like buy one of these lockers in our lab and try to do an exploration, and we found out that there are two pins inside, and you can actually like open up the front part of the panel, and there are two pins which are like the reset pin and the ground pin, and apparently if you short them, then the pin gets zeroized, and therefore if you press in like 0 0 0 0 0 0 0, the locker will open. Okay, so you see that that is the gap between what essentially the theory was giving, guaranteeing you, and what you ended up in doing. So you didn't really, like break, or you didn't have a faster way of, like understanding what is the pin, but what you ended up is doing a very easy attack, which essentially completely bypasses the security strategy. So therefore, right, there is a waterfall theory in security which says that, or in any design for that matter, that you have to analyze code, I mean, analyze, design, code, test, and release. But where often, like we kind of, like miss out is on the testing part. But in security, the test problem becomes even more difficult because you really do not know what the attacker will do, right? So therefore, it becomes extremely a difficult proposition to say that, like that I have, like tested my circuit and my circuit cannot be attacked. Okay. So therefore, there are different ways of doing that testing. So some of them say that, okay, let me try to be an attacker and try to, like try several ways of breaking it. And if that doesn't break, then the system is secure. But we have seen again and again, right, that really doesn't work because the attackers are often very smart. They always come up with a new technique through which probably we have not thought as a designer. But that doesn't mean that we will not invest our time in understanding the attacks, because that is extremely crucial to get an end-to-end security. So in order to do this kind of research, we set up this lab, which we called a secured embedded architecture lab, where we try to work on attacks and countermeasures, and like try to look into various practical aspects of security like IoT, cyber physical systems, and so on, where there are like several faculty members, and among which I am one of them, and there are several PhD students, masters, and so on. Okay, so there are also some students from NIT Durgapur who are also doing exceptionally good research in our laboratory. So we are very thankful to the NIT family as well. So it is extremely important to do, like analyze or put life into our research, and for that instruments are crucial. And we have this, like laboratory setup for doing, like side channel analysis, where we have got laser stations and other kind of setups to do analysis, IoT security, cyber physical system security, where we are trying to kind of set up a smart grid setup, a small smart grid setup to analyze the security vulnerabilities. Hardware forensics is another area that we are trying to focus, and I will try to talk briefly during my presentation. So these are some of the ongoing security projects that we are trying to work on, which are all important in the context of CPS or IoT, post-quantum security, hardware security, cyber physical systems in general, Trojan detections, and anti-counterfeit IoT security in a broader sense. And of course, like malwares and ransomwares, we all know that due to the COVID, right, we probably have seen much more malwares than in a normal situation. So in the hindsight, I would say that, like many of these security measures that are there, right, I mean, they are not adopted. And that essentially is the reason why we have these kind of breaches. So why are they not adopted? Because many of the security measures are actually an overkill. Okay, like they may be several passwords, and often we know that the passwords that we have, like you probably enter, are essentially not very strong. And that essentially implies that you do not really get a proper amount of security. But security, right, in the yesteryears was a little bit of less concern, but it has become growingly important. So ignorance in today's world is not really a bliss. Okay, and for example, there are reports which says there are several billions of money, or in general, like property, which is getting lost because of security mismanagement in around the world. So, for example, we have heard of ransomwares, okay, and the ransomwares, you can imagine that, suppose, right, if you have got a hospital set up, right now, we all know that medical is an extremely important situation. So suppose there is a ransomware which hits the hospitals, right, and starts to encrypt critical data, right? I mean, then and asks for ransoms, then that is devastating. So how do you really, like ensure that those are not really happening? Because they are happening again and again, and we are, like clearly being exposed to such kind of adversaries. So I hope that none of you have seen this screen on your computers getting flashed up. So this was, like when the WannaCry ransomware was around the world, which was essentially showing you that apparently if it gets into your computer, it will encrypt your important files. It will encrypt probably the boot sector of your computer, and then will ask you for ransom. And even there are situations where if you pay the ransom, you do not get back your coveted file. So you can imagine that how, like a simply a benign looking, like website or like a link that you are clicking can completely jeopardize, like not only your data, but as well as data now is becoming more and more crucial, it can kind of, like really be menacing. So talking about, like cyber physical systems. So this is the most, I would say, like a classical example of CPS in general. So this example was called as Stuxnet, or is family called as the Stuxnet in SCADA, which is essentially nothing but a supervisory control and data acquisition system, which essentially which is there in any control system. So this attack essentially targeted Iran's nuclear centrifuges. So the story of how the attack works is extremely interesting. So apparently around the nuclear power station, there were some people who were selling hardware tokens, which are in the form of USB sticks at a very low cost, with the hope that somebody from who is working in the nuclear power station will use those sticks, and it ended up in some people using it, and that essentially launched a malicious worm into the Iranian computing systems. Okay, and then what the malware does is basically it searches in the industrial control system. It was searching for the high speed centrifuges which are used to enrich the nuclear fuel. And then what it does, it does a morphism. That means it basically downloads a more recent version of itself for which there are no, like sort of known. I mean, there are essentially, I mean, these are kind of what are called as the zero-day attacks. And then what it does is it slowly tries to kind of sabotage the working condition of the nuclear power station so that eventually it becomes very late. So the centrifuges at some point of time starts to rotate at an enormously high speed, and then the complete and then nothing can be done because the nuclear power station is completely hijacked by the malware. So you can see that a simple hardware token which is not trusted can lead to the catastrophic consequences in a like a big critical infrastructure as a nuclear station. So why does these attacks work? So I will talk about this in briefly. So this is another famous example of like connected systems getting attacked. So so when we talk about like the modern day cars or automotives, right, are probably more computers than mechanical devices with several lines of codes which goes on in them. While there are nice safety mechanisms, but the security is still under research. So here is a very famous example which was published in Wired 2016 and also presented and demonstrated at Black Hat Security Conference. So apparently what it shows is that, as you can see in the photo at the top, the adversary has taken a complete control of your steering system. And you can imagine that if that happens on a highway, and then it basically issues commands through the internal network to the steering, brakes, and engines, and creates an accident, as you can see in the bottom diagram or bottom picture. Okay, so therefore you can imagine that like and these attacks essentially are mostly taking place through the infotainment system hardware which is there in the cars, and again can lead to dire consequences, right? So therefore, right, why so one of the like so we basically try to do a study about why such kind of cyber physical systems can be attacked, and here is a project summary that we are trying to do with Bosch, who is, as we know, is a quite famous automotive company. So here is a classical overview of the control systems where you have got the plant, the controller, and there is a feedback. So in most of these control systems, right, or cyber physical systems, there are some kind of residue detectors which basically tries to monitor the difference between the output of the plant, which the sensor gives, and the output of and essentially the output which is estimated from the previous sensor data. And then if this difference is below a threshold, then there is no alarm raised. But if that difference is, it crosses a specific threshold, so typically, largely these thresholds are static, and if it kind of exceeds that threshold, then an alarm is raised. But then can an stealthy attack bypass a static threshold-based detector? So exactly as we have seen in the Stuxnet example, it indeed can. So for example, here is a simulation that you can see that the purple line over here shows the residue. And you can see that what the attacker does is it surreptitiously or very, maliciously introduces small changes. And so it ensures that the residue is always lesser than the threshold. Okay, it is always lesser than the threshold, but you can see that the system state slowly starts to increase and it crosses the orange line, which is your safety bound. Okay. So therefore, this example shows you that it is indeed possible to synthesize such kind of attacks and can, completely jeopardize the cyber physical systems where, so such kind of threats are possible. For example, as we have seen in the example of the Stuxnet situation, and therefore we need to have suitable safeguards. So we need to have probably, for example, the data that your plant is generating, right? Typically, it could be from the sensors that you are deploying over there. But the question is, right, do you really trust that data, right? Do you really know that the sensor data which is being generated, right, is an authentic data? So, that essentially immediately brings us to the questions of authentication and security and so on. So a nice solution could be, let me encrypt all the things that are there and let me kind of, authenticate, but that will make probably the system so slow that you really cannot get a real-time performance. So it is a continuous trade-off between, the amount of security and privacy that you need and the amount of cost that you can afford. Okay. And that essentially is extremely important. And that is exactly what we are trying to kind of look into. The other kind of threats can also come from your computing systems. For example, recently, right, there was this famous news about Spectre and Meltdown, which essentially are a bunch of microarchitecture attacks. So all our computing systems, right, have evolved probably for 20 years, 30 years, and so on. But the primary focus was performance. Okay. So for example, you have got cache memories, you have got branch predictions, you have got several kind of artifacts in your computing systems. The whole objective of that was performance. So these attacks, which are called as Spectre and Meltdown, they targeted something which are called as so it's a collaborative work from Google as well. So which basically shows that or exposed critical vulnerabilities in modern processors. So they targeted in particular what are called as speculative execution. So we know that all our computing systems have a speculative execution. So and they support what are called as out of order execution. Okay. So, for example, when you are teaching, computer architecture or high performance computing architecture, we always see, that the out of order execution essentially is a very powerful primitive or powerful tool that has been invented by computer architects to enhance, the performance of your computing system. But here, the attackers exactly used that principle or that, artifact to develop a technique through which your passwords and our personal photos, emails, instant messages, or even critical business documents can be stolen because what happens in a very top level, right, when you're doing speculative execution, you are doing certain computations which you are probably later on you will not do it actually. But by the time you have done that, but by the time probably you will not commit to those computations later on. But within this time, since you are accessing illegal data or some data that you are probably not allowed to access, the cache, for example, may have temporarily that amount of information, and if the attacker, right, is able to read the data from the cache, then then that data which you are typically not allowed to access, probably you are ending up accessing it. Okay. So therefore, right, this can be also very have dire consequences on your personal computers, on your mobile devices, and in the cloud. And you see that all of these components you are using in some form of or the other in your IoT infrastructure. Okay. So how do you fix them? I mean, you can of course completely do a re-engineering, but that is not possible because this has come out of evolution of 20, 30 years, and therefore this is extremely important. So these class of attacks are called as side channel attacks because you are not really accessing it from the inputs and the outputs, but you are observing something, right? Maybe the speculative execution traces which nobody thought when they were designing the systems as well as the security solutions. So therefore, as I mentioned, that side channel attacks tries to address this gap between theory and practice, and it is very important in the context of in the context of cyber physical systems. So if we think that our problem can be solved by cryptography, then there is a problem. So there's a famous quote from Bruce Schneier which says then we do not understand cryptography and we also do not understand the problem. So we cannot just resort to cryptographic algorithms to give us a solution. We have to understand the system on which they are being deployed. So there are different attack threats which are possible, and of course we have got our humans, and it is probably impossible to design a totally secure systems with humans in it, but we will not be probably concentrating on them, but we will rather focus on the software and the hardware components which are used in IoT, and try to try to see that at least whether we can have a trusted hardware, and on top of that we can develop a software which is a software execution which is more reliable. So therefore, the broad message is that strong cryptographic algorithms are just the beginning. So if you can take your smart card, for example, which you are using it maybe in some kind of card accepting device, and if you are accessing, using say some kind of strong cryptographic algorithm like RSA, for example, and you are doing an input and output exchange, so mathematics guarantees you security till this point. Okay, but it may end up somebody is observing some kind of traces. It could be the power supply, the EM traces, or maybe something else through which the attacker can reveal the secret key in a trivial manner. So therefore this is exactly what we do not want, because we want that the guarantees which mathematics provided, so our security should be at par with that. And therefore we need to understand that how the crypto engineering takes place. Okay, I mean, we have a nice cryptographic algorithm, but if you do not implement it properly, then there can be trivial leakages. So one of the possible in our classes on hardware security, what we try to kind of illustrate often is a very popular example of how do you implement say an exponentiation algorithm. Say you are implementing say y power of k, where k is your secret. So as we know that in a standard textbook from Corman, or algorithm textbook, the way to implement y power of k is by employing an algorithm which is called as the square and multiply algorithm. So you basically do a binary encoding of k, and then depending upon the ones and zero sequences, you do a multiplication or you don't do a multiplication, and then you get y power of k. So this is kind of a very folklore algorithm and a very popular algorithm. But exactly when you are writing a crypto code or a security code, then you should not write the code in this manner, because if you are doing that, then you are doing a statement which is conditional on the secret key, and that can be exploited by an adversary. Okay, so this is a very simple example, but tells us that the way we train ourselves in algorithms, and when you go to write a security code, you have to take some extra caution so that you end up in implementing your codes in a proper manner. So therefore security nowadays can be a game changer. So I always like this by a very I like this slide because it shows that Intel, when they ignored Spectre, Meltdown, and so on, their stocks fell down by around 5%, whereas AMD was good. I mean, I do not really know that whether AMD did these designs on purpose, but this actually shows that security can be a game changer. Okay, and we often becomes more serious when it hits us in a bad manner, and it indeed shows that we have to ensure that our solutions are more secure. So that essentially brings me to the end of the first part of my talk, and then I will rather go into discussing about the second part, which is more getting into the details about side channel attacks. So we all know that IoTs are next generation networks, and I believe that in this workshop we have enough illustrations on this, so I will not elaborate on this. And there are billions of devices which are communicating, and it can revolutionize the quality of life. Life from the Indian context, it has got enormous applications: water control, food control, e-governance, pharmaceuticals, and so on. So right now, probably the IoT, if properly enabled, can be used to maybe disseminate the coveted COVID vaccine as well. But it is extremely important to integrate security in the IoT by developing novel secure protocols. Otherwise, there can be menacing threats. So this is a very famous paper. It was written by an Israeli group led by the great Adi Shamir. So Shamir is the S of RSA. So this was published in IEEE Symposium on Security and Privacy in 2017. So this shows an example where some kind of like automation bulbs or home automation bulbs, which are deployed by a company by a famous company, and it is actually marketed as Philips Hue, and they were like positioned in some companies in Israel. So you can see in the top diagram. Hello. Okay, so they were like deployed in a company in some companies in Israel, and the attackers in this university in from Israel, they demonstrated a very interesting attack on the IoT systems. So the paper's title is called as IoT Goes Nuclear, creating a Zigbee chain reaction. So what they did initially was they investigated the corresponding Philips Hue lighting system, and then they found out that there is a firmware inside these devices. So the idea is that these are smart bulbs, and as we know that these smart bulbs can be controlled and commanded only by people who are whitelisted to command them. Okay, and so what they do is that using a Zigbee, they authenticate themselves to through a like a switch, and the switch essentially is commanded by the owner of these bulbs. So of course you do not want to end up in your neighbor, like controlling these bulbs, and that is where security and authentication comes into the play. So what they found out is that in the hardware or in the embedded or in the firmware of these devices, there is a proximity detector, and the proximity detector ensures that you cannot control these bulbs maybe like from a 1 kilometer distance. So what they wanted is they wanted to update the firmware in these bulbs, in some of these bulbs which are installed in these machines. Okay, and then right, I mean, and in order so that like the proximity detector is removed. So but you cannot like install, or you cannot execute any, or you cannot update the firmware arbitrarily, because when you do that, there is a verification that is done on the hardware. So what they do is that they perform a check. That means they create a massive authentication code, which is called as the AES CCM mode, which is very popular and secure. And then the checksum is verified again, and only the verified like checksums will be allowed to execute. So therefore, right, they wanted to forge that. In order to forge that, they needed the secret key, and the secret key was a 128-bit AES key, which is essentially extremely difficult to obtain. So what they did is that they took this hardware and then they performed an analysis on that using the electromagnetic radiations, and from there they cracked the entire 128-bit key. So this is an example of side channel attack. And now once you get the key, you can essentially update the firmware without the proximity check. Now, once the proximity check is kind of removed, then these bulbs can be controlled from a distance. And then they showed a very interesting demonstration where there were drones which were flying around the building, and the bulbs inside the building were like displaying an SOS signal to show that they are completely being possessed. Okay. So there are more details in the paper which I'm not going to. Since the name is IoT Goes Nuclear, they showed that how one IoT device can like affect the other next set of IoT devices, and that can like infect even more. And I think if I remember, they showed eventually that they can actually create blackouts in a city as large as that of Paris using this kind of methods. So you can imagine that a simple potential side channel attack on the hardware device can form an attack surface which can lead to the complete collapse of the IoT infrastructure. So the question is, how do you really secure them, or what are essentially these techniques? Okay, so I think I already talked about this. So the question is, what are side channels? So the side channels essentially are therefore covert channels which leak information which the designers of the cryptographic algorithm did not consider. So as I said, that even a simple if-else statement in a programming language can lead to secrecy leakages. So here is a like a very simple demonstration of how a setup would probably look like. So you have got like various endpoints in the device. You have got the oscilloscopes maybe through which you are monitoring the power consumptions or the EM consumptions, and then this is the hardware on which your crypto runs, and then you try to do a statistical analysis of the data that is accumulated or that is being so when there is a code which is running on the hardware, you are trying to kind of observe maybe the electromagnetic radiations around this device, and then you try to do a statistical analysis of these traces to get the secret key. So that is essentially in a very high level the overall scenario through which IoT or like side channel experiments would look like. So therefore, for example, when if you are running, for example, an AES code, okay, or an advanced encryption code, and if you observe the traces, like this is exactly how it will look like. So you can see that on the left diagram, I show you the traces, and from there you can actually virtually count the number of rounds inside the algorithm. For example, AES has got 10 rounds, so therefore AES 128, you can see the 10 rounds by just counting. If you zoom down, you will see some more variations. So these variations essentially lead to an attack strategy, which are called as simple power attacks, which essentially exploits the fact that the variations occur because of the operation dependence of power. So for example, the simple algorithm that I mentioned, square and multiply. So there are two operations that you are doing, right? One is a squaring and one is a multiplication. So if the power consumption depend of the squaring is different from that of multiplication, then it can lead to certain category of attacks. So these are called as simple power attacks. On the other hand, there is even a stronger form of attack, which are called as differential power attacks. So these attacks try to exploit the fact that the power or the EM radiations or any other side channel manifestation also depends upon the underlying data, and that is essentially extremely difficult to prevent. And these are called as differential power attacks. So this was originally published in Crypto in '99 and opens up, like Pandora's box of several kinds of attacks. You can break AES or any other crypto system for that matter using these techniques. So how does this work? So here is a very top level explanation of how these attacks can be done. So for example, you can take any crypto engine which is running on your hardware, okay? And what you can do now is that you can feed several inputs like plain text, for example, and allow the engine to encrypt. So when it is encrypting, you observe the corresponding ciphertext, but you also observe the side channel trace along with it, okay? So these side channel traces are being stored in a squared matrix, and the squared matrix is like shown here as the matrix P. So you can see here that I have got encryptions of say inputs like D1, D2, so on till DD. Okay, so these are your various. I don't know whether you can see it here. Yeah, so maybe you can see my pointer here. So these are my inputs D1 to DD, and when it is encrypting, the corresponding power traces are denoted as say. So the first time when you feed the input D1, say, which is a plain text, you get a power trace, and that you write in the form of a matrix. So this matrix is shown here as like this part that is like P11, P12, so until P1T. So the T is the time instance on which you're observing, and this essentially looks like this power trace, for example, or the EM trace. Okay, so likewise for the second data like D2, for example, you are essentially observing another trace which you are essentially storing maybe in the second row of this matrix. Okay, so this way you build this matrix. This is what I called as the real matrix or the real power matrix. And now when you are basically also encrypting say D1, D2, DD, and so on, you also try to do something else. So what is it? Now you try to guess maybe a part of the key. So suppose you have got a 128-bit key which is 16 bytes, you do not guess the entire key at once, but you do something which is called as popularly the divide and conquer strategy. So you guess only a part of the key, maybe K1, okay? So you get maybe the 1 byte of the key. So this byte can take, like maybe K possibilities, so that K can be 256, for example. So you have got K1, K2, K3, and so on. These are all hypotheses of the corresponding key. So once you make an hypothesis, say K1, using this, right, you basically do a partial encryption, and then you apply something which is called as a powered model. So this powered model is a very popular terminology in VLSI, where we believe that the power consumption would say depend on the Hamming weight or Hamming distance or so on. And once you have that, then using that power model, you essentially build up which is called as a hypothetical power matrix. So this hypothetical power matrix means that every row here, for example, you can, or every column here will depend upon a hypothesis. So that means if I take K1 as my hypothesis, using K1, I will, I will calculate the corresponding column for, for all the possible inputs that I'm encrypting. So suppose I'm encrypting from D1 to DD, I will be doing, this hypothetical power estimation for all these D observations, and I will get something which is called as a hypothetical matrix. And then what I will do is I will take this particular column and I will start trying to correlate with each of these columns. Okay. The idea is that if my key hypothesis was correct, at some point of time, I will get a very strong correlation. But if my key hypothesis was wrong, then this correlation will look as if I am correlating two random sequences. Okay. So that way, that is a basic idea. Okay. Very simply put. And it tries to kind of, evaluate a correlation matrix, and the correct key is whichever maximizes that correlation. Okay. So that is essentially, I would say, the principle behind power attacks, or any side channel attacks for that matter, which basically tries to kind of distinguish your correct key from the wrong keys. So therefore, I mean, we essentially are also building up in developing an open source tool for doing that through our incubation that we have at IIT Kharagpur, which we call as ESP. And this is a tool that we have built to do side channel inspection of hardware devices that you are trying to deploy and engage in security applications. So the other popular form of attack are what are called as fault attacks. We all know that faults are menacing. Like suppose you are, if you have a very complex system, then there will be some form of bug or the other. So when you are doing encryption, for example, so you have got a plain text, and then you essentially get your, fault-free ciphertext, because you take the plain text, and when you normally encrypt, you get the fault-free ciphertext. But imagine that suppose when you are doing encryption, there is suddenly a change in the environment. So this could be, maybe there's a voltage fluctuation, and there could be, maybe some kind of, EM invasion or something like that. And because of that, and there can be many ways of doing that, but there is a fault that has been created. And this could be an intentional fault, it could be a malicious fault, it could be an unintentional fault. But the question is that once you expose this faulty ciphertext, then the attacker can analyze the fault-free ciphertext and the faulty ciphertext to get the secret key. Okay, so you can imagine that what you would expect that, okay, there is a fault, and let me just repeat the computation and go ahead. But what you have probably ended up in doing is you have ended up in divulging your secret key. Okay, so therefore you really cannot just go ahead, but you have to again kind of redo your key exchange and other things. So why does faults work? So I will again not go into the details, but I will just give you a very top level idea. So when you have got your encryption systems, so suppose there is a fault, and the fault essentially can be any arbitrary value, but when it propagates inside the cipher, it starts to exhibit, like some kind of interesting mathematical relations. As you can see here, that if you concentrate, say, on this particular diagram, you see that this is an example of the AES crypto system, by the way. You can see, if you observe here, there are nice mathematical relations, as you can see, among the fault states, which essentially the attacker will try to exploit and get the secret key. So to summarize, actually, I mean, so the idea is that these attacks even on strong crypto algorithms like AES works with only one single fault. So that means if there is only a single random fault that has been introduced inside the AES while if the AES encryption is taking place, at the correct place, only a single fault will reveal your entire 128-bit key. So you can imagine that, and the attack will take you less than 1 hour to perform. Okay. So therefore, I mean, and people have really taken this seriously around the world, and they are even, inspecting fault injections for automotives and so on. So here is a case study which essentially is, I believe, is very interesting. So which was reported at a fault conference where they showed that, suppose you are taking chips which are ISO 26262 standard, which are deployed in the MCUs, which are foundational units for the modern vehicles. And they are often certified with respect to what are called as ASIL. That means Automotive Security Integrity Level. And they are marked from levels A to level D. Level D means they have got the highest level of guarantees, okay, against attacks. So they have got protection against faults during normal operations. And they did a case study of how these ISO 26262 standard certified chips which are there inside your automotive vehicles can be bypassed by a clever adversary. So what they did is they, so the one of the ASIL D chips was an ARM Cortex R4 core, and the second one was a PowerPC chip. And then they tried to do two experiments. One is using a voltage glitcher, and the second one was using an EM glitcher. Okay, so EM glitcher means an electromagnetic glitcher. And then they did an experiment. So the experiments were in two experiments. So in the first case, as you can see in experiment one, they did an assembly to add up an internal register several times and then verify that whether the add was correctly done. And in the second one, it is a more of like an authentication check. The idea is that if the channel is authenticated, then you allow it to communicate, else you stop the channel. So then they found out, as you can see in this table, that in the first chip, using the simple technique of voltage glitcher, 87% of the cases were not being detected by the chip. And in the second chip, almost like 57% cases were bypassed when you were using EM based glitching techniques. Okay, and these experiments were done over several glitches, as you can see, like around probably 700 lakh glitches or 500 lakh glitches for both the chips respectively for around 3 weeks. So after a set of experiments, they found out that this is the statistics of the chips not being able to detect that there was a fault injection being done. And you can imagine that since only one fault injection is needed to bypass, then it shows that that many of these chips which are certified against for safety, they are not indeed secure. So therefore it shows that security and safety are not the same. So I think I will just take a bit of time here of yours to show you a demonstration of a side channel setup that we have to show you that in practice how these things would look like. So I believe the sound is just let me know whether the audio is heard, or otherwise I will just tell. So is the audio? Can you hear the audio?
Not yet.
Yes.
Yeah.
Sir, your voice is not audible.
Okay, so you can't hear the audio, right? So that is exactly what I was asking.
Just increase the sound. I just increase the sound, I think.
Okay. Okay, let me try this one.
Now it's increase more.
Can you hear it?
More, sir. Increase little bit more.
Okay, I think this is the maximum that I have.
Yeah, good. Yeah, that's good. It's audible.
So I just stop here. So you can see here that the normal computation is say 0x15 inside this. And now we will shoot an EM pulse and you will see that this value will change. Okay. So this, sorry, this is the Pro for doing that EM. Yeah. So you can see that now this value has changed to 9.5, and when you stop the injection, you will see again it goes back to the original state. You see the value again gets back to 0x15. So you can see that the effect of fault is so transient that it kind of comes and go, and by that time your security can get compromised. So we also try to commercialize this tool. So if some of you are interested, then please feel free to reach me. So this brings me to the third part of my talk, where we essentially look into the authentication of the devices in the context of IoT. So I think we already discussed about the fact that IoT has virtually no protections against attacks, and because of the seamless communication of information, it always is important that we need to develop low overhead techniques for authentication. We need lightweight solutions. So in IEEE Design and Test in 2016, we wrote a work where we try to look into physically unclonable functions or PUFs as a promising tool for security in the context of IoT. And I will be trying to talk about few things in that direction. So before we started to work on this, we have set up an IoT lab at IIT KGP where we try to look into the authentication of the same, like the various kind of IoT devices. Among one of them was these Philips lighting systems. So we found out that initially when the app was launched, their authentication was as follows. So what they did is that they took the MAC address of the device, which was used to whitelist, and then they created an MD5 hash on that, which is MD5 is a cryptographic hash function. And then the idea is that if that is kind of, like there's a whitelist in the breach, and if that matches, then that person is allowed to control and command the bulbs. But as we know that the attacker can also, who's in the network, right, can also get access of the MAC address of the devices, and then she can, like he or she or it can, like easily retrieve the username of the device by just trying all the possible MD5 hashes, and then find out, one of them will probably be successful. So when this was reported, this mechanism was changed, but it became even more worse. So now what is done is that there is a random number being generated, and that random number is communicated even in the plain text. There is no virtual encryption. So if the attacker can capture the traffic between the legitimate user and the Hue breach using some kind of, like eavesdropping tool like Wireshark and so on, then these whitelisted usernames can be obtained by a simple script written in a high-level language. So here is an example, quick demonstration of that. So here you can see the username is created at the time of registration. And while sending any command to the breach, the username is fetched by the Wireshark tool. And then you can actually, using the IP address of the breach and the username, the entire whitelist of the breach is exposed. So this is completely shows that there is virtually no good authentication in these systems. So how do you really fortify the IoTs through, like techniques which are low overhead? Because of course you have got, it's not like that people are not aware of the solutions which are, like mathematically strong and so on, but often they are not very, they are so complex and they are so costly that it is not affordable at the price that you would like to provide. For example, these bulbs were probably being sold at something like 15,000 Indian rupees at that time. So how do you really make security or authentication in the hardware? That is the question. I mean, can you really make your hardware trusted, or can you build your trust from the hardware? So in this context, there is a very promising hardware primitive which we tried to explore, which is called as the PUF. So I will try to talk about PUFs in details, or rather in reasonable details in the time that I have. So puffs are essentially, like a promising primitive which tries to operate as what I called as, like IC fingerprints of the devices. So just like we have got human biometrics, so similar to that, can we have, like fingerprints for the devices? So the idea is that if I take say two puff circuits and if I, if I deploy them on two hardwares, so the idea is that, and if I give a challenge to both of them, then the response of one of the device should not reveal to me any information about the response from the other device. So statistically, each of the puff outputs should be kind of, like unrelated to each other. And of course, they need to be, like satisfying some kind of quality in terms of cryptographic properties, like they should have a nice, like 0 and 1 sequences. It should satisfy the randomness requirements. It should be reliable and so on. But most importantly, they should be unclonable. So that means, right, I should not be able to write a machine learning model or a mathematical model which can predict what would be the response for an input that is not known. So therefore, model building attack is a very important threat against this class of circuits, and we need to secure against them. So in the top level, right, a puff would look like this. It is basically a challenge response mechanism. So challenge is the input that you give to the puff, and response is the output that you get from the puff. The idea is that from the input, right, you should not be able to predict what is the corresponding response simply because you do not have a closed form expression of the mathematical function for a puff. You don't have a, and the source of variation in the for the puffs, right, essentially stands for the underlying device. So for example, there is a CMOS scaling, there are variations in the physical parameters and so on, because of which there is an existence of randomness which is being exploited by these circuits. So for example, here is a simple experiment that one can try. We can take this ring oscillator circuit, which is nothing but these three inverters which are being cascaded and there is a feedback. And if you put it into an FPGA device, and if you, like depending upon the XY coordinates where this ring oscillator is situated, you will find out there are small variations in the frequencies. And if you compare, like across two devices, you will find out that they are still quite different. For example, you can see that across FPGA 1 and FPGA 2, the average here is around say 122, whereas in device 1 the average is around 135. Okay, so therefore there will be small variations in these, various kind of manifestations which can probably, like be used to work as a device fingerprint. So as an advantage, like so the puffs and the security primitives are very promising because it can reduce the cost, it can raise the security. So if you compare a world without puff with a world with puff, in a world without puff, you need to have a trusted party which will embed and test secret keys and store in some kind of non-volatile memory. But in a world with puff, the device itself can intrinsically work as a security. Okay, and the key never really leaves the IC's boundaries, and therefore the idea is that the entire device, right, operating as operates as your key, and the idea and the secrecy of the device is intrinsic to that device itself. So while it may look promising, but there are several kind of challenges. One of them, as I already mentioned, is the machine learning hurdle that we need to account for. But I mean, so okay, there are some other properties that I mentioned about puffs also, which are uniqueness and reliability. But I think the biggest concern is also, apart from machine learning modeling, is also on the reliability of the puff. That means if I take a puff and if I apply the same input again and again, it should give me the same response. Okay, and even otherwise, for example, India, for example, if you are trying to deploy puffs in India, and you can imagine that if you are wanting a mil grade security or mil grade solution, right, military grade solution for your hardware device, it can operate across a wide variety of temperatures. So you have to, like suitably calibrate them and so on, so that the device operates as expected. So, so therefore, what I will try to kind of quickly talk about is how do you really use the puffs in an IoT authentication. Okay, so here is a very simple illustration of that. So imagine that you have got a green device, and you have got the green device, which is essentially where your puff is situated, and and you have got a verification server, for example, where you imagine that like you have got a challenge response database which basically stores the inputs and the outputs of the puff. So why do you have a database? Is because of this reason, because of the fundamental definition of a puff, you cannot have a copy of the puff because the puff is unclonable, right? So therefore, at best, what you can do is imagine that suppose you want to do say 10,000 authentications for a session, you store the corresponding 10,000 challenge responses of the puffs in your verification server. So this was a classic authentication that was proposed in the original paper from MIT. And they said that, so this is given by a guy called Pappu, and they showed that, okay, let me try to use this as an authentication mechanism. So what you do is that you throw a challenge, and the device essentially uses its path to get the response, and then you verify that whether the response is true or not. But imagine that since, or think that since you have exposed the challenge and the corresponding response, okay, you cannot reuse this challenge because the attacker also knows this corresponding response for this challenge. So therefore, what you have to do is once you use this challenge response pair, you have to strike it off. Okay, and therefore for these types of puffs, there are two requirements. One is that since you are exposing the responses to the attacker, you have to ensure that the attacker is not able to build a model for the puff using these challenge response pairs. And the second is that your challenge space should be very high because since you are not reusing the challenge responses, we have to have something like a 64-bit challenge, which will give you say 2 to the power of 64 possible challenges, which is in that case a pretty large set. So these class of puffs are what are called as strong puffs, and they can be used, but at the same time they are not very easy to design. And more or less, the limitation of these kind of authentication mechanism is that since you are like exposing the bare CRPs in the verification server, that also can be potentially like subjected by an attacker. For example, if there is a malware or some kind of virus which infects the verification server, then the challenge responses can be exposed to the adversaries. So in one project with a company that we were working with, they essentially told us that can you come up with an authentication mechanism using puffs where the CRP need not be stored explicitly. So in that context, we tried to kind of work out a solution by combining puffs with public key cryptography. So what we want is that since IoTs are heterogeneous, and heterogeneous means that the devices are like very low end, but the servers on the other hand are complex and are powerful. So if you can develop a solution or an authentication protocol which is heterogeneous, meaning that the devices just does a puff computation, but the verification server can do more complicated computations, then that becomes appropriate for an IoT infrastructure. So what we did is we thought that, okay, let the devices now be like equipped with the puff. So you can see here that there is a node which is equipped with the puff, and there is a security credential generator which essentially engages in an enrollment phase. So that what you do is that you send challenges, get the responses, and store the corresponding hashed responses in the cloud. So note that when you are using the cloud, you need not bother about the security because you are anyway exposing it to the attackers, and you are not really bothered about the confidentiality because what you are banking on is this hash function. So you are banking on the fact that suppose like you are hashing the response of the puff, which is say RA and getting as PA, but like you are not storing PA and PS also on the cloud, but you are kind of suitably modifying them by doing some kind of computations which are based on the hash function and also on some kind of public key cryptography, which I'll not go in details, but you try to kind of like do a bit of public key cryptography and get these tuples which are called as CA, CS, A, and B. So what you stored in the cloud is the input that you are giving to the puff, okay? But you see that from CA, you have got no way of predicting what is the corresponding response because the puff is random in its behavior. So therefore, you can like store CA in the cloud without bothering about any kind of security leakages. So therefore, right now, what you do is you go into your verification phase. In the verification phase, suppose this node wants to communicate with a verifier. Then the verifier, like accesses this tuple from the cloud, CS, A, and B, and then does some amount of computation. Okay. So again, I will not go into the details, but what you do in the nutshell is that you try to get a pair of inputs. So for example, you get a pair of input denoted as QA, and you send it to this node. The node uses its internal puff and gets a response, which is a VA dash. And then you basically ensure that this VA dash is as per this tuple that has been stored on the cloud. So in this manner, you have got a two-phase protocol, one where you have done an enrollment and then you are doing a verification, and the verification can be done without the security credential generator, but by just accessing this information from the cloud, which is essentially pervasive, and you completely divide the requirement of like storing the explicit challenge responses at the verifier end. So the verifier also does not know what is the response of the puff, and therefore it can also not develop a machine learning model for the puff. So we try to kind of like use this technique for securing several IoT devices. One of them was these video surveillance cameras. So many of those video surveillance cameras, as we know, are not having security solutions, and therefore, right, one can try to do a meet in the middle attack where the adversary sits in between, right, and can sell steal data. But if the camera is now equipped with this puff, for example, as we show here in this diagram, then the person cannot inject stale data simply because it cannot respond, or it cannot be respond with the expected response from the camera, because it doesn't have the corresponding hardware for the puff along with it. So we try to do a security analysis, and of course like an estimation to see that whether it fits the budget, and we found out that overall latency of our solution is something around 480 millisecond, and the power consumption is around 0.044 watt. And using that on a standard elliptic curve based security solution, we try to combine puffs with ECC to get an end-to-end security. So we also looked into like some other security like aspects. For example, many of these wireless protocols, there is a famous as we know, like an attack which is called as crack, which essentially was also demonstrated on a WPAT tool, and it shows that they can also be vulnerable. So again, we try to use the concept of puff to secure against such wireless protocols or attacks. So I will quickly, and this was published in WWW in 2020, and I will quickly give a video demonstration of this. So this is an example of showing how a fake access point can be detected and using again the technology of Puff. So this is a joint work with Wipro, with whom we are trying to develop this IoT solution along with the Puff. So another project that we are trying to work on with DRDO is on, like how can two hardware devices communicate. So you can see here that as of now we still have got two unclonable devices, and the problem is that since we cannot have a clone of that, so it cannot really, like we need a, like a mechanism with public key infrastructure and so on. So what we are trying to see is, suppose you have an ad hoc network, right? And if you want really two hardware devices to communicate, can there be a mechanism of doing it? So the motivation of this comes from, like the fact. So this is just an, like a very hypothetical analogy. So you can see here there's a tree, like which is called as the mad tree, which is there in this botanic garden in Calcutta, which is very close to my hometown in Howrah, where you can see that every tree, this tree has got every leaf which is distinct. So that is the idea of puff. But if you see, like for example, there was an article which was at some point of time, it was believed also that every snowflake is identical. But there was an article which shows that actually there are possibilities of twin snowflakes. So this kind of, like led us to this idea, thought process that can we have two hardware devices which are twins and not really unclonable. So this brings us to this idea of what are called as cryptophasia. So cryptophasia means it's a language of two twins, and apparently there is a term called cryptophasia, which means that this is a language which only the twins can understand, but others cannot. So we try to kind of develop a solution using what is called as physically related functions, and you can show here a very quick demonstration of this. So here you can see that there are two hardware devices, okay, device one and device two, and we call this concept as physically related function, not physically unclonable function. The idea being that although these two devices are different and distinct, right, but there is a small challenge subset for which the responses would be identical. So if these devices know that, like then what they can do is now they can, without any trusted third party, can do a peer-to-peer communication with security embedded in the devices. So you can see that node A is communicating with node B, and node B is sending without any prior agreement, by the way. Okay, so there is no prior agreement being done, and then they are able to establish a session key. So this is a solution that we are trying to see whether we can upscale up to an IoT and, like develop a solution for ad hoc networks, and which is secured against replay attacks and meet in the middle attacks and so on. But this is a work in progress. So I think I have got another 10-15 minutes, probably more, to talk about the final part of my presentation, which is on the cloud aspect, where we know that several amount of data is being continuously being put into the cloud. So how do you know that privacy is guaranteed in such scenarios? So particularly now, probably all of us will understand this, that, suppose if you are using this some kind of COVID for COVID, like you are using, like you are, suppose our medical data is getting over into the cloud, we do not want that data to get divulged to everybody, right? So there is an amount of privacy that we would look into that. So therefore, that brings us to the other end of IoT, okay, and that is very important. And one of the ways in which people say that, okay, let me encrypt the data and keep it onto the cloud. But if you encrypt the data, then you cannot process on the cloud. You cannot do machine learning, you cannot do analytics, you cannot do search, and so on. So this brings us to this concept of what is called as searchable encryptions. So can you encrypt and yet you can do some kind of computations? Okay, and so before I go into how to do searchable encryption, let me see how to not to do searchable encryption. So this is again, like a snapshot taken from a very famous company who promises to do searchable encryption. But then in quietly, right, in one of their overviews, they write that to provide you with the most relevant results possible, we then decrypt your search term and securely request results from our search and content partners. So if you are using this, for example, in server like Google, you exactly do not want that, because you do not want even Google to know the database on which you are searching, or for the things that for which you are searching, right? You do not want it to know what are the keywords that are being getting searched. And there are various techniques which have been proposed. One of them are what are called as fully homomorphic encryptions, which are largely impractical. And then there are some solutions which are extremely, like security, I mean, they're weak in terms of leakages. So we try to do a, like a sort of a trade-off between them. Eventually, what I want is I want to do an, like a search, like I want to search for, like say all emails with, suppose I have got an encrypted mailbox, and I want to search, like for things like Alice, Bob, and so on, but all of them should be encrypted. Okay, so this essentially, so I will try to give a broad overview behind what this means. Okay, like what searchable symmetric encryption means. So it means typically that suppose I am the owner of the cloud. Okay, I'm the owner of the data, not the cloud. But what I will do is I will take my data and I will have a small cryptographic key. Using that, I will encrypt that information and I will outsource the data onto the server. So suppose if you are using Dropbox, like for example, for keeping your pictures, then you will encrypt your pictures and keep it onto the Dropbox. Okay. So now, suppose you want to search for a picture with a certain keyword, maybe, like suppose you went to some place and you want to search only for those files where that keyword occurs. So then what you will do is you will encrypt those keywords, and these are called as encrypted tokens. So therefore, with the files being encrypted and with the encrypted tokens, can you do search? That is the whole problem. Okay. And there are many solutions we have proposed. So one of them is what is called as the oblivious cross tag. And I will, without going into details, is a solution which is proposed in crypto in 2013. So what they said is that, okay, let me take all the keywords like W1 to say WN, and out of them, I know that there is a specific keyword, say W1, which occurs with the least frequency. Okay, suppose you are making a search like, like for cinema, which starts with say Soumitra Chatterjee and like Hindi cinema, right? You will probably know that the relative ordering of the frequencies among them, and according to that, you know exactly the keyword which occurs with the least frequency. So first, what you do is you make a search with that keyword, and then among this reduced set, you try to do something which is called as cross tag. So you basically try to see that whether those databases on which this keyword W1 occurs, whether W2 occurs, W3 occurs, W4 occurs, and so on till WN occurs. Now, because of these crossword leakages, because you see that the server is really learning this, so there can be very strong attacks which are called as file injection attacks. Well, I will not go into the details of this, but what we wanted to develop is we wanted to develop a solution. And again, like this is a technique which is called as hidden vector encryption, which we implemented using a very simple technique which are called again as like symmetric key encryption. So you can instantiate a hidden vector encryption only with using primitives like AES, and you can do a search which is very fast. So quickly talking about the results here, now we can like suppose you have got a 60 GB of database, right? You can do a search for like which will probably take you less than 1 second. Okay. So again, like before I stop, let me just to give you the idea behind this, I will give you a quick video demonstration of this. So think of this as maybe the Google search that we always do, but the only difference is that now we are encrypting those files and putting out on the server, and the tokens on which you are doing your search, which are the keywords, they are also encrypted, and still the search will take place. Okay, so let's see. So that means suppose you are making a search on AES, ECC, and RSA, but the server does not learn about these keywords. Okay, so you can see that from the server end, whatever files are being returned here are shown here. All of them are encrypted. You can decrypt, you can download it and then decrypt it. Okay, so this is essentially just a quick demonstration of how eventually probably things will be disseminated on the cloud, and we will be able to do like suitable search on that. So something else that we are also trying to work on is whether we can have hardware accelerators. So we are trying to build a system where there will be FPGA clusters, and this entire processing will be done on them, and so that we have a very fast encrypted search taking place. So future directions, we are, like we know that India is the largest importer of hardware. Probably that will change, but right now it is so. And therefore we need to develop techniques for doing what are called as Trojan detections. And we all know that we have got, like many people we are very anxious that many of our hardware devices can get corrupted. So we are trying to develop an in-house flow for intrusive method detection. So with DRDO, where we have procured a scanning electron microscope and FIB, and using that, you can see that this small chip that we have, for example, this is a MEMS chip that has been designed by our electronics department. And when we zoom it, we can zoom it and see the internals at a high resolution of something like 10 nanometers or so. You can see internally the antenna, which probably can be used for, like communication, which is not told to you. So we are trying to develop such kind of techniques, disassemblers, and so on with the help of DRDO and also with other government agencies. So we want to basically answer this question on whether your hardware that you procure is secured. The other thing that we are also working on with ACRB is on developing a solution for fully homomorphic encryption, which is a holy grail in computing. So as I said that we have some way of understanding how we can do search on the cloud, but we want to also give support for arbitrary computations. So with this, can you hear me? Hello.
Yes, any questions? Participants, any questions from your side? Saurabh, any question you have to ask? Saurabh Raj?
Hello, can you hear me?
Yeah.
Hello.
Tell.
Yeah, sorry. So I think there was a small power cut in my home, but I think now I'm back. So yeah, just to conclude, hardware security in IoT is of utmost importance in modern society. We need to develop expertise in security, embedded systems, VLS architectures, networks, machine learning, and so on. IoT is very interesting in that sense because it provides us a variety of platforms. So on one hand, you have got the resource constrained things. You have got the pervasive clouds on other hands, which offers different attack surfaces. Sidechain attacks, inability to support costly ciphers, eavesdropping, replay, masquerading, poisoning, coalition. These are some examples of attacks. We strive to develop novel tools and solutions for overall security. We want to enable hardware primitive for like an end-to-end IoT security. So finally, I would like to conclude with this famous saying from like which says that a chain is no stronger than its weakest link. So if there is a small link which is not strong, then the overall security of IoT would collapse. So if some of you are interested in hardware security, then this is an NPTEL online. I mean, it's right now not probably I'm not floating it on NPTEL, but the entire set of lectures are available on YouTube. And I would like to say thank you for your attention. And in particular, I would also like to announce that if there is there is somebody who is interested to collaborate on fully homomorphic encryption also, then we have some open positions for that as well. So with this, I would like to say thank you for your attention. And if there are any questions, I would be very happy to address.
Thank you, Professor Mukhopadhyay. Participants, any question from your side?
Sir, for health data, what type of, I mean, I'm working in the field of health data. What will be the better approach to handle security of health data?
Okay, so that's a very nice and important question. So so I've seen like as I mentioned that when we talk about health, right, in particular the concern is privacy, I guess, because what we want is that that information should not get divulged, and still you should be able to do processing and analytics on that data. So therefore, right, I mean, depending upon the scale that you have in your hospitals or in your place, right, people are trying to develop solutions using fully homomorphic encryption. So fully homomorphic encryption is essentially a holy grail in computing, through which you can apparently do arbitrary computations. So you can do additions, you can do multiplications, you can run machine learning tools, and so on. So having said that, fully homomorphic encryption is still now under research, and while there is a significant progress, more needs to be done. Okay, but I would say that you should look into the literature on FHE or fully homomorphic encryption. Okay, and try to ensure that you can do computations, and at the same time you are not revealing your confidential data.
Thanks a lot, sir.
There is lot of noise. So yeah. Okay.
Yeah, no.
Okay.
Emma.
Good morning, sir.
Yes.
My question is about the hardware security. You said hardware security is the most important one for communication in IoT. And most of the example I might have seen that are peer-to-peer communication. Suppose if there is a multicasting, what will happen? And I have a doubt how to identify the fake MAC address, MAC points.
Sorry, I did not. I actually missed few parts of the question. I understood that you said that. Yeah, can you just repeat once more your question, please? I missed because there was a lot of noise.
So about that false access point.
Okay, fake access point. Okay.
Yeah, fake access point. How do we find that? And most of the example I have seen that is a peer-to-peer communication. The examples peer-to-peer communication. Suppose if it is a multicast, in that case, how we can do that hardware security? Sir? Is it necessary to have that the devices are trusted one, and how we can measure that is there any algorithm is
yeah, so if you, for example, look into the literature of wireless security, or like in general ad hoc network, or see overall, like if you look into the things on key agreement protocols, for example, in general, you will find out that these concerns which I mentioned, the replay attacks and the meet in the middle attacks, these are very generic concerns. This is got nothing to do only with peer-to-peer networks as such. Okay, so therefore, right, even if you are talking about like other kind of communications, then these attack vectors are still possible. And actually, if you see the classical protocols like Kerberos and so on, right, they are not developed on a peer-to-peer network. Okay, so now the problem that is, of course, like these are not new, these are old as well, right? We already had these kind of problems in the olden days. The only, I would say that the challenge nowadays, the challenge that we have now when we are talking about IoT or in general IoT CPS security, is the fact that many of these devices are extremely resource constrained. So therefore, right, you cannot run a powerful crypto engine like maybe like an elliptic curve crypto or maybe a public key infrastructure easily on these hardware devices. More so, say tomorrow you will be having like the post-quantum threat as well, like you have the threats from quantum computer and so on. So therefore, right, you need to have a solution which is kind of scalable and deployable across like various kind of engines. And largely, like we have seen that many of these attacks take place because the devices that are like being deployed in an IoT infrastructure, they are lying on in the wild, right? They are lying on in the roads, they are lying on in your buildings. If you're talking about smart meters and so on, it is there along with the attacker. So the attacker, like what it can do is that it can try to take these equipments and it can try to enter the entire network. And once it enters the network as legitimate, then it can do havoc. Okay, so that is the concern.
Okay, sir. Thank you, sir.
Saurabh Roy, any question?
Yes, sir. This is Sanjeev
One by one. Okay, Sanjeev. Just I am calling back you again. Saurabh Roy, ask your question, then I'll go to the Sanjeev Kumar. Saurabh Roy, am I audible? Saurabh, we are not getting.
Yes, yes, sir.
Please raise your question. Okay, Sanjeev sir, you can now ask the question. Sanjeev sir. Saurabh, you have raised your hand. Will you ask any question? If so, then ask. Otherwise, lower your hand. Okay. Any participants?
Hello, sir.
Yes.
I hope so. Am I audible? So, can you suggest some of the simulators for in incorporated the security protocols? Can you suggest any simulators to work on it?
You mean so typically, right? I mean, when we do these security inspections, right, then we try to use so like use standard eavesdropping tools, right? For example, so like we try to, for example, work on like this Kali Linux and Wireshark and such kind of eavesdropping tools to inspect the security or insecurity with the IoT protocols. Okay, but as you see that the protocols that we develop for with puffs, right, are largely developed in-house by us. Okay, so for example, we try to like for example integrate the OpenASL library with puffs and so on. So these are done because since you are changing the hardware, right, you have to essentially do it kind of ground up. Okay, so that is what we try to do. But if you are evaluating, say, existing IoT solutions, then you can use the like tools which, for example, Kali Linux is a good place to start looking at, I would say. I think I had some of them in my slides, so you can probably look into that.
Okay, sir. Thank you, sir.
Participants, Mr. Saurabh has some question. Saurabh, can you try now? Okay, sir, one question. Here's a chat box. We got it. That chat box, one person raised the question. Am I audible, Professor Mukhopadhyay?
Yes, you are audible. I'm also trying to see it actually. Yeah.
Okay. He's asked this question in case of strong puff. Sometimes it happens that strong puff also modeling attack is possible. Then how we can prevent it?
Okay, so that is a very good question. So of course, like I mean, it's a continuous process about like so. So let me just unshare the screen because then probably I can see the questions. I cannot see the questions anyway.
Sure.
So yeah, so basically, like the idea is that of course, right, this is a continuous process of developing model building different paths. So right now, while there are like the classical paths where subjected to model building attacks like arbiter puffs and so on, but there has been a huge evolution of puff designs, right? So for example, there are nowadays puffs which are, although I would not say that they are like robust completely against machine learning, but if you want to do an ML attack on them, you will require several thousand challenge responses probably, or maybe million challenge responses to model them. Okay, so that also gives you a kind of bound, like on how many times you can use those puffs without like changing some kind of parameters inside the device. But like having said that, this is an ongoing field of research where we are trying to like develop ML resistant puffs completely, which can be completely secured. So by the way, I mean recently in ICCAT we had a paper where we published on like what we called as PUFG. Okay, so taking the name of PUFG, which is not great actually, but we call that as PUFG. So the idea is that we try to do what is called as a pack analysis. So pack, as we know, is a theoretical like measurement of the quality of the puff. against ML attacks. So we try to develop a language in which you can write the path and then describe the path. It's a high-level language in which you can describe the path, and then we use our tools or automated tools to do an approximate analysis on the amount of security against theoretical machine learning. So this can be a mechanism of quantifying and also comparing the paths. So there are, like some good paths that have been developed. For example, there is a path which was developed by called as iPath. If you have seen iPath, or so people are develop, recently in ISI also there was a path which was developed from their school, which is also pretty robust against machine learning attacks, I would say.
So it may possible that when any path-based protocol, so multiple times when the protocol is run, there is a chances that hacker or attack, that means can get the challenges from multiple challenges from, and they get the modeling attack is possible.
No, so the idea, yes. So
yeah.
what we try to do often, or what is typically done in the industry, if you see these protocols that I was talking of, the response is never exposed to the adversary. So there is always a cryptographic hash function, or like a hash that has been done, and after you do the hash, right, you basically store that into the some form in the cloud. So therefore, the attacker, right, doesn't get access to the raw response of the path, but takes an output of the hash. And once you do that, right, then the machine learning attacks cannot work. Okay, or it's very hard to. At least we do not know how they will work, I would say.
Okay, but if the attacker access the paths, then what will happen in these cases?
Yeah,
if there is a chance to access.
The hardware, the hardware does both, right? The hardware does the path computation and also does the hash. Okay, so whatever comes out of that is the hashed response of the path. Okay, so
if the attacker access the path.
Yeah, so the attacker, first of all, does not have access to the raw response of the path, because if you want to do that, you need to have invasive techniques for doing that. And the second thing is that the path is also designed in a manner so that the ML resistance is very high. Okay.
Okay. Thank you. Any other questions? Already so many questions here answered. Participants, any questions?
It is the whole point. So
yes, sir. Hello. Am I audible, sir?
Yeah, there's an echo, but you are audible. Yes.
Hello.
Yes, Professor.
You are audible, the echo, but
am I
ask the question immediately. Yeah, audible. Ask question.
Yeah, sir. In case of path-based IoT security, the path we are using, if the IoT devices are deployed mostly in the adversarial environment. So if any adversary gain the access of the IoT device where the path is embedded, so for that case, the adversary can also gain the challenge response pair. Yes. So that challenge response pair we are storing in the server, will that be enough secure if the adversary gain the physical access of the path?
Right. So if you can, I mean, I probably did not have the time to go into all the details, but there is a paper that I cited in my presentation, which was published in IEEE TDSC, where we give you the description of the entire solution. You will see that we have tried a plethora of machine learning attacks on these path designs. Okay, and then even then, the probability of guessing a bit or response of the path using the good ML techniques, right, is not significantly higher than 0.5, which is a random guess actually. Okay, so of course, like if you do a very bad design of the path, then, or a straightforward design of the path using FPGA tools, it will not work. We have to do a bit of like hand-holding and like hand wave design on the path so that the ML resistance is guaranteed. Okay, so we are not saying that it cannot be done or it cannot be ML attack, but at least like the common ML attacks will fail. Okay.
Okay, sir.
Okay.
Okay, sir.
I mean, that's the challenge, right?
Mukhopadhyay,
yeah.
Yeah. So I think no further questions we are getting. So we can stop the session here. So thanks a lot, Professor Debdeep Mukhopadhyay, for this eye-opening session. The vulnerability of the IoT in light of the hardware modeling attack is nicely described and lot of research opportunities, which is also the direction of such type of FDP is explored by him. I thank all the participants are really benefited, and also such by the brainstorming session. Nice explanation with some video graphs also. Again, thank you, Professor Mukhopadhyay, for such a most valuable talk and
Thank you all.
synergize our FDP. Okay.
Thank you all.
Okay.
Thank you very much. Thank you.
Thank you.
Bye.
Sure.
Stay safe.
Bye. Okay.